Okay, as I said, today we're going to speak on how to pass from energy statistics to energy balances, but also we'll touch the topic of CO2 emissions and try to understand how CO2 emissions are estimated starting from an energy balance data. So I would like to start as every time with sharing a live pool with you. So if you can connect to www.menti.com, I will soon share the screen and you can so put the exact code for this live pool. Oh, should be this one. Can you see this? So the code for this pool is 78 71 85. I'll let you the time to connect, and in the meantime, I'll read the first question. So this is just a question to see if you already have some knowledge on what we are going to see today, but it is of course not a big issue if you still don't know, because we are going to speak about that. I see there are some grammar mistakes. Instead of units, we wrote units, but this is of course physical units. The question is it possible to have a statistical difference, so a difference between the quantity reported on supply and the quantity reported on all the demands of energy equal to 0 in a statistic table, but for the same country or the same year, having a statistical difference that is different than 0 in the related energy balance? I see one person already answered, and we see a yes. I'll let you the time to continue to answer. Since we are not many today, we are 9 now, so people are continuing to connect. This is a good thing. Someone is saying, no, we cannot have a difference. So we have seen a bit this topic last week, but today we'll see a bit more. Try to reflect and think about how do you pass from a statistic table, so in physical unit, for example, oil products in barrels or in tons or in liters, for example, to an energy balance that report the same table and the same figures, but in energy unit. So if you remember well, we use the calorific values. That is exactly the energy content of a specific fuel per unit of physical quantity. So it can be, for example, kilojoule per ton. You can see only 3 persons answer, so wait 1 minute more so everyone can start connecting to Menti, and then we can go faster for the next questions because the code doesn't change. I remind again, the website is www.menti.com and the code today is 78 71 85. You can also use your phone if you have a phone close to you, or the same laptop you're using to follow the training. The nice thing of this feature is that we'll see the results live, as you have seen in the other webinars. So it's quite interesting to see what people think. I may for this one give the answer, and the correct answer actually is yes, because of calorific value. Someone just answered no, but now that I give the answer, it will be easier for the rest. The answer is yes, because calorific values can differ by flows, and the same products can mix with other products coming from other sources in the consumption side. And so to have a statistical difference that is 0 in both physical tables and energy tables, we will need to have a perfect use of calorific values in terms also of weighted average, different products, etc. So this is something that is difficult to achieve in reality. So it is possible to have a different statistical difference in statistic tables, so in physical unit and energy unit. And this is due to calorific values. But we will see the answers with Aidan that will show you an example in a table. So if you go to the next question, now we can go faster because I've seen that at least 5 people are able to answer. Now I speak again about energy balances. And the question is, if you see in a balance table a positive number in the total column, so the last column that takes the total of all products of a transformation flow, so for example, the production of electricity or a refinery where you have input of primary products and the output of secondary products like electricity, is that possible to have a positive number? We also see this answer quite in detail with Aidan in the presentation. But it's nice that we start thinking about that. So as I say, I can say again, the total column is the column that regroup all the products. So for example, you have electricity, you have natural gas, you have biofuels, and they're all summed in the total column. Then the transformation flow can be, for example, let's take the example of electricity production. So in the transformation flow, you will have the input of the different products used for electricity production, and then the output of electricity. I will give you an intel on that. The inputs in energy balances in the transformation sector are reported with a negative number to show that this is something that will be consumed and transformed to something else, while the output, like in this example, the electricity, are reported with a positive number. So they will show with a plus in front of them. Only one answer, but 5 people were connected, so maybe you are guessing and trying to think what is exactly the question, because I understand it's not easy without seeing a table to explain that, but no worries, we will show graphically this example much better later on. Some people are saying yes, and this means that the transformation efficiency is very high. Some people are saying no, totals are always negative because transformation efficiencies are always lower than 100%. So 3 people answer. There are 2 more that at least can answer because they answered the last. One other say the other answer. So no, transformation outputs are always equal to the inputs and totals are always equal to 0. Okay, I think we have a winner here. More or less we are at the same level, but most of the people said that no, is not possible because transformation outputs are always equal to the inputs and totals are always equal to 0. The real answer is actually the one that received only 1 person, 2 now, maybe after I was saying that. And this is because totals are always negative because the efficiencies are lower than 100%. This is because, for example, if you have natural gas for electricity production, you will have this negative number and the input is, for example, 100, let's say, megajoules. But when you transform this to electricity, the electricity produced by the 100 megajoules of natural gas will be lower than 100 megajoules because you have losses. And so the efficiency is lower than 100%. This will cause the total column to be always negative. But we'll see that more in detail later. And this is a really important and also complicated part of reading energy balance, but will give you the opportunity to be able to estimate the efficiency of the transformation processes that are happening in your country by looking at the losses that appear somehow in the total column as a negative number. So let's now go to the next question. This is about tomorrow. So tomorrow we understand is a Muslim holiday, and in Ethiopia the offices will be closed in the government at least. So what we want to know is if you can answer here, if you're available tomorrow and you have an internet connection, or if you prefer to postpone. If you prefer to postpone, is it better for you Monday or Tuesday? So we have 7, I think more or less is the same number of people that answered before. Of course, this is not representative of the whole course because we are 20, but as we have seen after the problems that happened in Ethiopia the last month, we have lost some of the participants because they maybe have now other priorities or still not have a proper internet connection. But I think if 3 people want to postpone out of 8, we should postpone. And so the decision we will take is to have the training on Monday instead of tomorrow, because it's better that also these 3 people that represent at least a third of the people that are participating in this program now will have the possibility to attend live and put their questions. So I hope it's okay for everyone, but I will send an email later, and you can also send me an email if Monday is not okay for you. But I think for the moment, we can say that Monday will be the day for the next training where we'll speak about modeling. So now I will go back to the presentation and we'll start again. Oop. Here we are. I hope you can see my screen. And now we can go to the next slides. So what is the agenda today? We'll first see what is an energy balance, just right now. Then we'll see why it is important to calculate energy balances when you collect energy statistics, and what is the functionality and the usefulness of energy balance for doing analysis of the energy sector and markets in your country. And then we'll speak also about the indicators you can calculate using energy balances data, and also what are CO2 emissions and what they can tell you about your country. Then Aidan will walk you through the technical part of this whole topic, so how we calculate the energy balances and the importance of calorific values to do that. Then he will lay out an energy balance, and we'll have a focus on the transformation sector. As you have seen in one of the questions, is a bit of a tricky part of the energy balances. And finally, we'll see with data how you convert or you estimate actually CO2 emissions starting from energy balances data. So let's start now with what is an energy balance. Energy balance is a table that has a compact information of the energy sector in your country. You will have all the different products in the flow, in the columns. So for example, here we can see coal, crude oil, natural gas, hydroelectricity, geothermal, biofuels, electricity, heat, etc. And here we have the total column that we discussed before. An energy balance has a common energy unit. As you can see in this example, we are in tons of oil equivalent, and it is for one only year. An example is 2018. The only energy units that are used for all products permit to compare by product and by flow. So for example, for this country that is Senegal, you can easily tell what is the most fuel used in the consumption side. So the TFC is total final consumption. And here we can easily say that in Senegal, oil products are the most consumed fuel, followed by biofuels and then electricity. So this is the good thing, the good point of using the same units. You can compare what are the fuels, for example, that you are more reliant on. Then on the rows, you have all the different flows that go from supply, so the production, the trades, they use on international aviation and the marine, and then the transformation sector, the energy sector, own use. So for example, a power plant that is using some energy for its own functioning, the losses, and finally, the final consumption by different sectors, so industry and all the subsectors, transport, etc. You can also add additional information, and this we do at the IEA, providing also the output of electricity by each fuel in, for example, here in a different unit that is more common to be used in electricity, in gigawatt hours, etc. So this is the flows that I just mentioned. As you can see, is a compact information, a picture of 1 year of energy supply, transformation, and consumption in a country. So it's a really compact piece of information that can tell you a lot of a country or a region if you can read it. As you can see, this is the total products where we sum all the products on the final column. An energy balance can also be shown in graphic formats. This is an example of the Africa Sankey flow, where we can see from the left to the right the representation of the energy balance in the terms that we'll see. Firstly, the supply side, where you can see the production, for example, in the left side of oil or coal, of biofuels, for example. The imports as well, as you can see, for example, oil imports, coal imports, electricity imports. And then moving from the left to the right, we'll see all this supply coming from production and imports, how is consumed in energy balance. There are some that will be exported, a part that will be put in stocks, so that will be stored for use in the next year, a part that will be transformed, for example, in electricity station, and you will see some products are going here to be transformed in electricity or heat as well. And then you will see where each product go in the final consumption. For example, you see some products go to transport, we can see here to industry, we can see some electricity going in the different sector as well. This is a graphic representation of an energy balance. It is also interesting to see because it can give a quick picture of the country energy sector, because the width of these lines, let's say, or arrows, is directly proportional to the quantity of each fuel. For example, here we can see that for Africa, biofuels and oil products are the biggest flows supplied. And if you go to the right side, we can see that biofuels are actually the most consumed fuel in final consumption, because most of the oil that you can see in production for Africa is exported, as you can see here, to other countries. So say that, we can continue and try to see why it is important to calculate energy balance. I think looking at what is an energy balance, we already know why it is important, because it has a lot of information. But let's see to list some of the main features of the importance of an energy balance. So it allows to calculate the total energy supply and consumption. As you can see, we have the same units, so we can sum all products and we can sum also all the flows. It allows to study the patterns for the whole energy market in once, because it tells us all the different products and flows in one only picture. It helps also to weight the different energy sources, as we have seen in the international or regional mix, because you can see what is the highest source, for example, of supply, what is the highest source consumed in a specific sector. It shows also the consumption across the different sectors of the activities, and it allows to calculate many interesting indicators such as the energy intensity, the dependence on energy imports, the energy security, the consumption per capita, CO2 emissions, etc. So it is a piece of information that, coupled with other calculation or other socioeconomic indicators, permits to have a very interesting set of indicators that can be helpful to analyze your country energy and emission figure. It is also good for quality control, because as you can see in the transformation line, you can estimate the efficiency and understand if there are problems with the data. For example, in the question we had, if you have a positive number in the total in a transformation flow, it means that there is maybe a problem, because there are no losses, but there is an energy gain. So maybe there is a misreporting either in the inputs to the transformation. So for example, you're reporting too few natural gas, or you're reporting too much electricity produced with this product. But we can see that after with Aidan a bit more in detail. Let's see now how you can use the energy balance data to calculate interesting indicators while you couple, for example, with common indicators like the population or the GDP. You can, for example, calculate your energy production divided by the total primary energy supply. So you will know how much of the energy you supply to your country is produced by you and how much is instead imported. So this is a really important indicator, and you can do it by fuel. So for example, for Ethiopia, you can try to see for energy products, for oil products, sorry, you can see that the production in Ethiopia is quite low because you don't have a refinery, while the supply, okay, with energy balance is not exactly what you can do, but it will tell you that you are reliant on imports from other countries. Or you can look at the net oil imports by GDP. You can look at your energy supply by GDP. This is the energy intensity of a country. So it's how much energy is consumed or transformed or available to in your country by GDP, so by your economic output. This will tell you how much energy your country in a specific year needs to produce 1 unit of GDP. This is really dependent on the structure of the economy of your country. Of course, if you have really heavy industry, this number will be higher. And if you have more services in your economy, this number will be lower. But it's a very good indicator to follow and to track the efficiency of your economy, the intensity, let's say. Then you can see how much energy per population is consumed. You can see many other interesting indicators. For example, how much electricity is consumed per capita, per person in your country. So that, let's try to see an example on energy intensity. So we have seen energy intensity is total primary energy supply divided by the gross domestic product. If we see that both indicators separately for Ethiopia, we see that the GDP has been increasing quite a lot during the last 10 years, let's say at least 20, from 2000 to 2017, while the energy consumption remained more stable. It just doubled from the 1990s, while you can see that GDP increased by 7 times. What does it mean? This means that we have a decoupling from the energy used in the country and the economic growth. This can be because of different reasons, and the most important are the structural effect, that this means that there has been maybe a change in the economic structure of the country from, for example, industry through more services sectors, or from heavy industry to less intensive industries. And the second reason that can move that is also the energy efficiency. So for the same industry, you became more efficient. So you require less energy to produce economic output. So in physical terms will be to produce, for example, a ton of steel, you require less energy because you improve the technical efficiency of your steel production assets. So you require less energy to produce your product that then will be sold and will generate an economic output. So these are the main 2 reasons why TPS, so total primary energy supply, and GDP can decouple. What does it mean if they are decoupling this way? That the energy intensity, that is the ratio between them, is decreasing. So in Ethiopia, we see that the energy intensity of the economy since 1990 has been decreasing sharply. Then we can use this indicator, for example, to compare in 2017 different countries. As we can see, Ethiopia has a quite high TPS per GDP compared with other countries, but this includes also solid biofuels, so the use of traditional biomass in the country. And so it could be a bit misleading when you are trying to understand the intensity of your economy, because this is a completely different kind of use of energy. It's not industrial energy, it's not generating economic output, the use of traditional biomass. And since in Ethiopia and also in Sub-Saharan Africa, this use is quite high compared to other countries, it can put noise in this indicator. But you can compare between different countries. As you can see, the OECD countries normally less intense than non-OECD because of different reasons. Can be structure, can be energy efficiency, but can be also the energy mix. As we have seen for Africa, the example of using biofuels is putting some noise in this interesting indicator. Then we can see the self-sufficiency of a country, so how much you produce divided by how much you supply of energy in your country. So as you can see here, we have put OECD, non-OECD, Sub-Saharan Africa in blue, and also Ethiopia in red. We can see that Ethiopia, using this indicator, as it is, using the totals, is 100% self-sufficient. But again, remind that here we are including biofuels and waste, as you can see in this figure. And for Ethiopia, biofuels and waste represent a very, very high percentage of the total primary energy supply. This means that if you calculate these indicators using the total for Ethiopia, you can see that Ethiopia is self-sufficient in its energy supply. However, we need to pay always attention because of the noise that biofuels is bringing. And this is a really typical thing that happens in sub-Saharan Africa and in Africa in general. So something that can be done to solve this is recalculate this indicator, but removing the biofuel and waste. And let's see how this will look. If you do that, actually Ethiopia from 100% self-sufficiency will become only 20% self-sufficient. So it means that Ethiopia, if we exclude the traditional use of biomass, provides itself of the energy that it consumes only by the 20%. And this is mainly because of hydroelectricity production. If we also remove hydroelectricity from this figure, Ethiopia is not able to provide for its own energy. Indeed, all the oil products that you consume in the country are coming, for example, from other economies. So you are importing most of the fuels. So if you exclude biofuels and hydro, you can see that most of the products are not coming from the production line in the year balance, but are coming from imports. So these are really interesting indicator, as I said, but need to pay attention when you use it. For example, international organization could publish it as a total, as you've seen, but it can be misleading because of these different noise that are brought by different energy trends or patterns that specific countries could have. And you can see that sub-Saharan Africa is actually very, very self-sufficient, but this is mainly because Nigeria and Angola are very strong oil producers. And so the production line in their balance will be really, really high. However, also these countries relies on imports for finished oil products, because even if they produce a lot of primary crude oil, this is mostly exported to be refined in other countries and then re-imported as final oil products. This is a very important, actually, energy problem for Africa in general, because there are many resources in the continent, but the infrastructure for the transformation of these energy resources in final energy products is lacking. And so you are reliant on other countries. But you have seen that this has been addressed by many development banks, by the African Energy Commission. Actually, the AFREC is doing a lot of work also on trying to address this infrastructure lacking on the midstream for the Africa energy sector. So let's continue now. I hope I'm not giving too much information, but I wanted to be clear that these are nice indicators, but you need to know exactly how they are calculated. So if you know your energy balances, you know your country or the country you're analyzing, you're able to decouple the different factors that are affecting your indicator and maybe calculate one that is more representative or what you wanted to know. Then you can also calculate residential consumption per capita. And again, here we can do the same example. You can see OECD countries' consumption per capita. So what is consumed in the houses of people is much higher than what is consumed in Ethiopia, for example. And here we're also including primary solid biofuels. But what happens if you exclude that? Because we say, okay, let's focus only maybe on electricity, natural gas, and modern energy uses. We can see that the difference and the gap is even higher. And for example, Ethiopia consumes a very, very low share of what a person in the OECD is consuming because of lack of electricity access, because of lack of access to clean cooking technologies and fuels, for example. So this is also the same example. We have a nice indicator, the residential consumption, but we need to pay attention also what we include in and what we want to see. What are the figures or the analysis that we want to do with the data that we are using. Now we can speak a bit about CO2 emission. Now I just show some figures and then Aidan will give you the important information on how we arrived to calculate this. These are the global CO2 emissions since 2000 and to 2017. You can see that the OECD share is very high, but it reduced from 56%, so more than half in 2000, and now in 20 years after, today is almost 37%. So now it's less than half. This is because non-OECD countries' emissions have been increasing very fast at a pace of, in average, 2% per year, as you can see in the dark blue. And if you want to see Africa, is the green part on the top, and I divided Africa by sub-Saharan Africa as well. We can see that the percentage in global emission is still very low. So we are at 4% only today of total global emissions, but the annual increase is actually quite high. We are increasing at a pace of 3.5% per year in average. So these are interesting things that you can see. You can see, for example, you can tell with this data that Africa contribution is low, but if we continue on this trend, increasing at 3.5%, probably Africa impact on global emissions will increase. So this is good because it will tell people that we have many tools to put in place to build a more sustainable energy system in different countries. Now we can see, for example, the same CO2 emission, but by sector. Where are these CO2 emissions coming from? And if we compare, for example, globally, if we sum OECD and non-OECD, we can see that electricity and heat generation combined with transport make up almost 2/3 of global CO2 emissions. So it's a very, very big part of it. And this is even more in OECD countries, sorry. This has also been increasing because there has been a huge electrification since the 1990s, or since, in this case, comparing with 71. So more use of electricity, so more emissions are coming from electricity. And if you look in sub-Saharan Africa, electricity generation represents a lower share for different reasons. Of course, there is the lower access to electricity, so there is a lower share of electricity production, but also because of relatively higher share of renewable sources, mainly hydro. For example, Ethiopia, electricity generation emissions are 0% because it's coming mostly from hydroelectricity and other renewable sources. There is some combustible, but it's really minimal. If you can see the same figure, but we allocate all the electricity that is consumed in the different sectors, and we allocate the emissions to this sector. For example, the industry is consuming some electricity, and we reallocate the power production emissions to this sector, depending on how much electricity is consuming, the figure change a bit. So you can see in this case, in the OECD, buildings, transport, and industry represent each of them more or less 1/3 of the emissions related to fuel combustion. While in the non-OECD, we can see that industry alone represents more than half. If you go to sub-Saharan Africa, interesting to see is that transport remains clearly the highest source of emissions. So this is mostly road transport and the use of gasoline and diesel in the road transportation. Now let's see what we can do after, again, even more with these CO2 emission data. We can also do some really interesting analysis. This is some work that also Aidan has been doing for a lot of years, and it's quite interesting. You can see in red your CO2 emission index, so how much has been increasing from an index of 100 in 1990 to today. You see in the non-OECD countries has been increasing quite fast. And then you can decouple this in trying to analyze the different factors that brought to this change in CO2 emissions. For example, we can easily see that in the OECD, we have a strong decrease in energy intensity, this purple line. We have a carbon intensity decreasing. This means that the energy mix used in OECD is getting more and more renewables. You have less fossil fuels and more renewable energy in the share, while the population is increasing as well as our wealth, so GDP per population. So when you have all these factors, you can see that the OECD has not been increasing that much, and luckily lately is also coming down to levels on the 1990s. And this is because besides there has been population increase and wealth increase, the energy intensity, so due to efficiency measures, but also to the different structure of the economy, so having more services and less heavy industries, as well as the better mix, the more renewable mix of energy, permitted to keep these CO2 emissions lower. The same thing we can analyze the non-OECD, where actually the population growth, that is the GDP per population, so the wealth, has been increasing very fast from the 1990s. Actually now a person in the OECD have almost 2.5 times what he had in terms of GDP per capita in the 1990s. So this has been bringing our CO2 emission very high in non-OECD. Then the other factors are more or less canceling each other. So the energy intensity index is more or less making out of the increase of population and the increase in carbon intensity. So in the OECD, in average, there is a bit more fossil fuel use than before. If we see like for Africa and for Ethiopia, we can see that population actually increase is the main driver of CO2 emissions in Africa. In Ethiopia, it's a combination of different factors that is bringing emissions up. There is population, but there is also the wealth increase, so the GDP per capita, as well as an increasing carbon intensity index. This is because Ethiopia is mostly reliant in hydro and traditional biomass. And if there is a small increase in the use of oil products, for example, for transportation, the carbon intensity index will increase drastically. But it's not that you are doing bad on this side. It's just that you didn't have in the 1990s the same access, for example, to or the same use of road transportation and so oil products, but a high share of hydro and biofuels. So say that, I think I'm close to the end of my part of the presentation, and I would like to go back to see some live pool questions for you before I pass the floor to Hayden. I hope you can see my slide now on the Mentimeter, so menti.com. You can go again to menti.com. The code is exactly the same. And now what we want to know is, we have seen many indicators and etc. And what we want to know if you worked in your country to calculate and report some energy indicators, for example, coupling energy data and activity data, or socioeconomic indicators, etc., for your country. If you can just write it down in the pool. So we'll have a picture of different indicators that you have been working on. For example, you calculated energy intensity, or you calculated CO2 emission per capita, or you calculated and published an indicator of residential electricity consumption per capita. Still not answers. Remind the code is the same as before, 78 71 85. Same website as before. If you didn't work on any of these indicators, you can also write it. You can say, no, I didn't work. But maybe we'll have a picture of different things. And if you didn't, but you have the data to do that, you could try to start working on GDP growth. This is also a really interesting thing. It's not coupled with energy data, but is an interesting figure that should be used also to be compared with your increasing energy demand. As we have seen, they are kind of related, and when they decouple, the energy intensity is changing. Only one person, waiting for some minutes more, because if not, we'll be late, and I know for you is a bit late this time that we are proposing. Energy consumption period, greenhouse gas emissions. That's great. So we have already some experts on greenhouse gas emission calculations. Carbon dioxide intensity, fuel intensity. Wow, now we have a lot. Household fuel intensity. That's great. So I see that you're already doing a lot of work on energy indicators in your countries, energy or socioeconomic energy indicators. But as you've seen, there are many opportunities to do even more. If you have good quality data collected, if you have the access also to other related socioeconomic data. And I hope the example we gave today give you ideas to do different analysis or to use the data on a different work, or maybe that this can feed your work with different ideas. And also, I think you can share with us, if you did any of this work that you are showing now, if you have a report or a database that you publish, it will be really appreciated if you can share it with us. We are really happy to look at your work as well and see and learn from your analysis for our own knowledge growth. So now that you're doing this, really interesting, many different indicators, we can go to the next question, which is about CO2 emission. So this is introducing what Aidan is going to tell you more in details. The question is, if you have an energy balance and you have a reasonable level of granularity in your energy balance, so by different flows and products, mostly products maybe, are you able to estimate your country's CO2 emissions from fuel combustion? The answers are yes. You just multiply the total energy consumption by a fixed conversion factor. Then you can say, no, I need more data to be collected. And finally, you can say, yes, you can use the standard IPCC carbon intensity applied to each of the fossil fuel burned and then sum them. So what is your opinion on that? But no worries, Aidan, we show you how this is done by the IEA and how it is supposed to be done also on the IPCC guidelines. Yeah, you have 2 answers already. 3 answers, sorry. And the carbon intensity for each fossil fuels is an indicator, let's say, or a conversion factor that tells you how much CO2 emissions are released when you burn a unit of energy of each fuel. So you will see different fuels at different carbon emission factors. That's great. We have 7 answers and most of you got it right. Indeed, you need to use a specific carbon intensity for each of the fossil fuels. If you apply a fixed or average carbon intensity to the total consumption, you might have some mistakes, unless your carbon intensity indicator is already taking into account the energy mix in your country. Let's go to the next question. Now it's just trying to order these different fuels from the most emitting to the least emitting. So for you, what is the most emitting among these fuels? Charcoal, liquefied petroleum gases, fossil coal, natural gas. Let's try just to order them depending on how much they will emit for unit energy. This takes a bit more time because we have to select. So we have some answers again. Charcoal is the first. Now is the second. So coal and charcoal are both at the top. LPG is third. And natural gas is fourth. How many people answered already? 3. So let's wait 1 second more and then we can maybe quickly discuss it. But I will be really quick because I think I took already a lot of time and Aidan need to tell you the most important things that you need to hear today. I was just speaking about how I use the data, what is good about the indicators, and why it's nice to have this data, but Aidan will tell you how you prepare this. That is the most important part. So now I think I can just comment it. We have fossil coal first, charcoal, LPG, natural gas. This is more or less okay. The only thing I will comment is that charcoal is of bio-origin. So when we calculate the CO2 emission from fuel combustion, we consider that the emissions that you release when you are burning the charcoal are sustainable because reabsorbed back by the biomaterial, so in this case, wood, so trees, that have been growing before you produce the charcoal. So this is, of course, depend on the use of the forestry. So if you are deforesting your country to produce charcoal, there will be some impact in the CO2 emission that are not neutral. But when you calculate the CO2 emission from an energy balance, you want to limit and take some hypotheses. And the hypothesis we normally make is that charcoal has zero related emissions because it is a sustainable, it's coming from bio energy. So it has been absorbing the CO2 in the atmosphere, in the forest, and then it's being released, but absorbed again by the trees that will grow again in the same place. So I think I'm done with the questions. So I will exit here and I will show again. I think it's better actually that Aidan shows his screen already, so we can directly start with his part of the presentation. Thank you very much, Aidan, to be with us today. As I said, Aidan has been working in the IEA for many years and is a real energy statistic expert. But you can present yourself, maybe.
Sure. I think you have to stop sharing before I can share. A little pop-up is telling me. So yeah, good morning, everyone. My name is Aidan Kennedy, and I work with Gianluca in the Energy Data Center at the IEA. I currently work on electricity, but I've also worked on balances in CO2 and or D&D statistics at various times. So glad to be with you here today. So I'll just try to share. And, okay, can you see my screen? Jean-Luc, can you see? Yep, good. Okay, so so now I'll take you through the steps involved in calculating an energy balance. So the first step in creating an energy balance is to convert all of the basic energy statistics data by product into a single unit so that we have comparable information for all products. In basic energy statistics, different fuels are collected in different units. We could have tons of coal or cubic meters of natural gas, and both of these are physical units. However, for an energy balance, we want all of the data to be in energy units. And most importantly, we want all of the data to be in the same energy unit. Therefore, we convert the data using calorific values. And a calorific value is simply the amount of energy contained per unit of fuel. And we use calorific values to convert between physical and energy units. As we use both physical quantities and calorific values to calculate the energy balance, it's important that we collect and use good quality calorific values. For instance, this country has an ideal commodity balance with zero statistical difference between supply and demand. However, if we look at the energy balance, we see that there is a statistical difference of 200 here. And this is because there is likely an issue with the calorific values that are used. So if we look at the calorific values, we can see that the calorific value used for consumption is 20 terajoules per kiloton. However, the values for production, imports, and exports are all in the range of about 22 to 25 terajoules per kiloton. Therefore, it's possible that there is a problem with the consumption value, that maybe it's too low. So this could be worth double checking. So as you can see, calorific values can also act as a check on the data quality when we create an energy balance. So we need to collect both good quality physical data, but also calorific values if we want a good quality energy balance. So now let us look at more detail at the principles of an energy balance. So when it comes to creating an energy balance, there are a few methodological choices that we can make. And some of these, such as the choice of unit, are simply a matter of preference. And they don't really make a difference to the balance itself. However, others, such as the choice of methodology, can have an impact on the numbers. I will go through these in more detail on the following slides. However, the main methodological choices are the selection of a common unit with which to create the energy balance, the choice of using net or gross calorific values, the selection of the calorific values for each product, the choice of what constitutes the primary energy form of some of the energy forms, such as hydro or wind, and finally, the choice of the appropriate methodology for calculating the energy content of these forms. In addition, although not mentioned here, you also need to decide on the time periods covered. For instance, do you use a fiscal year or a calendar year? And this is important to know. I know at the IEA, most of our data are in calendar years, but a couple of countries use fiscal years. And so the analysts are always very interested in knowing exactly what the data cover. And also you would need to know if you're making any adjustments for temperature, for heating degree days or cooling degree days. But we don't apply these adjustments at the IEA. So firstly, the choice of unit. Any energy unit can be used. However, for historical reasons, the IEA uses the ton of oil equivalent, which, as the name suggests, a ton of oil equivalent has roughly the energy content of 1 ton of oil. However, obviously oil varies from country to country. You have heavy oil or light oil. So we use a standard definition, and a ton of oil equivalent is defined as 10 million kilocalories. And that's the unit used by the IEA when we create our energy balances. However, another frequently used unit is the terajoule. Next, there's the choice between using gross or net calorific values. And most fuels can have a gross and a net calorific value. And the difference between the two is the latent heat of vaporization of water. So simply put, when you burn a fuel, you produce water and CO2. And the heat of vaporization is the energy used to convert the water from liquid into vapor. And in many cases, this energy is lost during power generation. It literally just escapes up the chimney as steam, and we lose this energy. And you can't recover it unless you have special equipment installed, such as condensers. So the gross calorific value will tell you the total energy content of the fuel, but the net calorific value will tell you the useful energy content. So the net calorific value for oil and coal is about 5% less than the gross, while for natural gas, the difference is about 10%. Now, some countries do use gross calorific values in their balances, but here at the IEA and in the United Nations Statistics Office and in the statistics offices of the European Community, Eurostat, we all use net calorific values. The choice doesn't matter too much, but it's good to be aware if you're comparing different balances, you have to really know which choice is being used. So next, there's the calorific values. So calorific values can vary by product. For instance, gasoline has a different calorific value than fuel oil. However, these values are not fixed. As natural products, calorific values can vary from country to country and also across time from year to year. In addition, they can vary within a country. For instance, the quality of fuel used for power generation might differ from that used in the residential sector. So for coal, the IEA uses specific factors for each of the main types of coal. So for anthracite and lignite, subbituminous coal, we have different calorific values. But we also have different calorific values based on the use. So different values for production, for imports, exports, electricity generation, blast furnaces, etc. And these are supplied by the national administrations in the coal questionnaire. For natural gas and crude oil, specific factors again are used for production and for imports and exports. And again, these are based on consultation with experts in national administrations. And for oil products, the IEA applies regional calorific values. So now we know how to convert combustible fuels into energy units. So we use calorific values to convert tons, for instance, of coal production, supply and demand into energy units. We can calculate how much coal is used in a power plant based on the tons of coal consumed and the calorific value. But what about nuclear or hydro or geothermal? So for these fuels, we know how much electricity or heat is produced. However, we don't know what the inputs were, as there were no combustible fuels used. However, when we're making a balance has to balance. If there's outputs, you need inputs. So we need to make an assumption in deciding what the inputs or the primary energy used for these products are. And this is important because you need to know the primary energy in order to calculate total primary energy supply. So here we have to make some assumptions. So for each of the sources listed here, they're non-combustible fuel sources, so nuclear, geothermal, solar, hydro, wind, wave, solar thermal, and solar PV. There's a need to define the form of primary energy that's used. So here we know the outputs, but to complete the balance, we need to define the input. And there's a number of ways to do this. For instance, for hydro energy, we could decide between the kinetic energy of the falling water as it enters the turbines, or the electricity produced. For nuclear energy, the choice would be between the energy content of the nuclear fuel rods, the heat produced in the reactor, and of course the electricity produced in the nuclear reactor as well. And for instance, for solar, you would have the choice between the solar energy that is hitting the solar PV cell and the electricity produced. So there's a number of choices, but at the IEA, we've adopted a principle in that the primary energy form should be the first energy form downstream of the production process for which multiple energy uses are practical. And in principle, this means that we either define the energy as electricity or heat energy. So in principle, this means that we assume that the heat input is the primary energy form for nuclear, geothermal, and for solar heat, and that electricity output is the primary form for hydro, wind, wave, and solar PV. And this, of course, means that we have to make some assumptions about what the efficiencies are. So now we have defined what the energy content, what the form of the energy to be measured is. However, we have to decide on a method by which to calculate it. And there are two main methods that can be used. There's the physical energy content method, which is what's used by the IEA. And there's also the partial substitution method. This was used in the early days of creating energy balances, but it's not really used any longer. So the physical energy content, the method that we use, it makes a link between the physical energy content of the primary energy source. It tries to link the input with a real world event. So for instance, for nuclear generation, we have defined the input as the heat production in the nuclear reactor. Now, we don't always know what the precise efficiency is. However, we can make an assumption. From data sources, we know that nuclear reactors in Europe are about 33% efficient. So here we can just make an assumption based on the electricity output and assume that this was produced with 33% efficiency, and then we can back calculate the heat input. Similarly, we can do the same for electricity production from geothermal. We assume 10% efficiency. And for heat production from geothermal, we assume 50% efficiency. While for hydro, wind, and solar PV electricity, we defined electricity as the primary energy form, so that essentially implies that we're assuming a 100% efficiency. So by using these assumed efficiencies, we can back calculate the primary energy content or the energy input, and that allows us to complete our balance. So this is the method that's used at the IEA. The alternative method was called the partial substitution method. And in this method, you would use the efficiency for another fuel. For instance, you could use the efficiency of a coal power plant. And then you would assume that the electricity produced from hydro, solar, wind, etc., was generated using that efficiency and back calculate the inputs. Now that sounds a little strange, but there was a logic to it. It had the advantage of smoothing out the swings in TPS that would occur with countries with large amounts of hydro. So using the physical energy content method, we assume that the efficiency of hydro is 100%. But for instance, imagine that in 1 year there wasn't a lot of rainfall, so a country needed to use coal instead of hydro. Now coal would have maybe an efficiency of 30 or 40%. So that would mean that the total primary energy supply would be much higher that year because they are using a different fuel source. And this, in countries with large amounts of hydro, this could cause large swings from year to year in the TPS. So by using a fixed efficiency of the coal plant, you would smooth out those variations from year to year. However, the downside of this is that the choice of the efficiency you use is really subjective. One country might use coal, another country might use natural gas. And it would also depend on the technology. Maybe some country has a very efficient plant, other countries have less efficient plants. So it makes it difficult to compare like with like. So for this reason, it was abandoned in favor of the physical energy content method. And in addition, the physical energy content method has the advantage of actually having a link with a real world efficiency or a transformation. So if you have any questions on that, send them through in the chat. I know that's sometimes difficult to explain. So now let's move on to the layout of an energy balance. So here we see a typical balance. The columns represent the various products and the rows represent the energy flows. And there are three main blocks of flows, as Gianluca already explained. So you have supply at the top, transformation in the middle, and finally consumption at the bottom. Obviously this has been cut off. There's a lot more consumption rows that are hidden from view here. So the supply block shows the main flows of energy entering and exiting the country. So we have production, trade, stock changes, and international bunkers. So by summing the values in the supply block, we can determine the primary energy supply for each of the various products. And then by summing all of the products, you can calculate the total primary energy supply for the country across all products. Now, there are a couple of important conventions and balances that it's good to be aware of. And the first is production. So only production of primary products is reported in the production row. Production of secondary products is reported under transformation. And this is done to avoid double counting. So for instance, this country here has an oil refinery, so it's a producer of oil products. However, you can see here, there is no production of oil products shown in the balance. The production is shown as an output in the transformation row. So on the production line, we see 0 production of oil products because oil products are a secondary product. And similarly for electricity, you will see 0 production of electricity in the production row. And again, you have to look at the transformation row to see this output. So for the refinery, in the oil refinery row, you will see inputs of 170 kilotons of oil equivalent, or sorry, 1,070 kilotons of oil equivalent, and outputs of 985 kilotons of oil products. So that brings us to another important convention, and one Gianluca mentioned earlier, and that's signs. So in the transformation sector, inputs are shown with a negative sign and outputs are shown as a positive sign. So if we wanted to, now that the data are in the same unit, in an energy unit, we could calculate the efficiency of transformation here by dividing the outputs, 985, by the inputs of 1070. And I did this earlier, it's about 92% efficient. So that's one use of an energy balance, is that it allows us to calculate transformation efficiencies. And so the other 8%, or the losses, are shown over here in the total row. So similarly, if we look at the electricity plant, the electricity column, here we can see inputs of coal and hydro and other fuels, and outputs of electricity. And again, over here, we see the transformation losses. And finally, again, these are losses, so they're shown as a negative sign, as Gianluca mentioned earlier. If they were positive, this might indicate that there is a problem with the data, because you shouldn't have greater than 100% transformation efficiency. So again, this can act as a useful check on the data. So to summarize, in the supply section, production of secondary products are shown as 0. And in the transformation section, inputs are negative and outputs are positive. And transformation losses are shown in the total column. And finally, total primary energy supply can be obtained by summing the supply of the various products. So some key takeaways on energy balances. So energy balances are important sources of energy data. They pull together data from all of the fuels into a single table. In addition, data are in a common unit, so they're easy to compare, and this allows ease of comparison across different fuels. However, a balance is only as good as the data it's built on. To borrow a computer coding term, garbage in is garbage out, so the quality of the energy balance can't be better than the quality of the data that are put into it. So good quality energy statistics are vital. And again, it's important to remember that energy statistics, both energy statistics and calorific values, are important. Sometimes people put a lot of effort into collecting the statistics and don't pay attention to the calorific values, but as we saw earlier, they are both important to create a good quality balance. And balances are also useful because they allow us to run checks on the efficiencies. So for instance, we can check the efficiency of transformation in a power plant or in a blast furnace, and we can compare those efficiency with previous values in other years. So we can check the year-on-year changes, or we can compare them with expected values. And so if these efficiencies deviate from expectations, it can also act as a check on the data. So this makes a balance a useful validation tool. And finally, they provide the foundation to generate a lot of useful data and indicators. For instance, CO2 emissions estimates, or the high-level indicators that Gianluca spoke about earlier. So now we'll move on to one of the uses of energy balances, and that's CO2 emissions estimates. I don't know, Gianluca, did any questions come through? If I should stop now, or if I'll just move on to the CO2 section.
It is okay. There was a question about CO2, but I answered typing, so people can look at that. But you can go through. I guess more questions maybe will come out about the reporting of transformation in the balance, probably.
Yep.
We'll see.
Okay. Okay. So moving on to CO2 emissions. So why is CO2 important, or why do we calculate CO2 emissions estimates? And it's basically because of the greenhouse effect, as we all know. So just to give you some background on it. So when solar radiation from the sun reaches the earth, about 50% is reflected. It just bounces off the atmosphere, or it's absorbed by the upper atmosphere. And about 50% reaches the ground, where it warms up the land and the ocean, and this keeps us warm and sustains life. However, after warming up, the Earth then releases some of that heat back into space. However, rather than passing through the atmosphere, some of this heat is captured by the greenhouse gases in the atmosphere, for instance, CO2, methane, and water vapor, before it can escape. And this is actually a really important process because it's a natural background process. And without it, the Earth would be about 30 degrees Celsius colder than it is today. So that would pretty much make a lot of the world uninhabitable. So we have to be all thankful for the greenhouse gas effect. However, the problem is that we're raising the levels of greenhouse gases in the atmosphere far above the pre-industrial levels. So they're capturing more and more of this heat before it can escape. And as a consequence, we're warming up the world. So the latest IPCC assessment report, that's the Intergovernmental Panel on Climate Change, their latest report showed that releases of CO2 and other greenhouse gases are causing the planet to warm. There's strong evidence to suggest that this is due to human release of CO2 emissions and not any other, it isn't just a natural variation, that it is humans that are causing the greenhouse gas effect to increase. And this report found that without action, the planet will likely warm up by 4 degrees Celsius by the end of the century. So the most important man-made greenhouse gas is CO2. In fact, CO2 emissions from fuel combustion are responsible for over 60% of total man-made greenhouse gas emissions. Now, unfortunately, levels of CO2 emissions are still rising, and emissions have roughly doubled from 15 gigatons of CO2 in 1971 to over about 33 gigatons of CO2 per annum in 2016. So emissions are still rising, and they have doubled over the last about 40 years. Now, there's been a lot of international efforts at reducing emissions, and this began in the early 90s, most notably with the Kyoto Protocol, and more recently with the Paris Agreement. So under the Paris Agreement, countries announced their intention to limit the global average temperature increase to below 2 degrees Celsius, and to make efforts to limit it to well below 1.5 degrees Celsius. So as part of this process, each country determined their own initial target for the period 2020 to 2025 and submitted those to the United Nations Framework Convention on Climate Change, or the UNFCCC. And that's a UN body that oversees the climate change process that's based in Bonn. Now, these targets were known as Nationally Determined Contributions, or NDCs. And global progress towards the overall goal of limiting the temperature increase to below 2 degrees will be formally reviewed in 2023 and every 5 years thereafter. So when calculating an official greenhouse gas inventory, all sources of emissions are covered, not just energy. Other sources are also taken into account, such as emissions from industrial processes, such as cement manufacture, emissions from land change use or deforestation, emissions from waste. So in landfill, when rubbish is dumped into a landfill, it emits methane. And there's some other niche emitting sectors. So in a greenhouse gas inventory that's submitted to the United Nations as part of the Paris Agreement process, all of these 5 sectors are covered. As Gianluca mentioned earlier, when we're calculating CO2 emissions from fuel combustion, we consider renewables such as charcoal or renewable biomass to have 0 emissions. And obviously, if charcoal is made in an unsustainable manner, then it's not really environmentally friendly. However, there are associated emissions. However, these would be accounted for under agriculture, forestry, and other land use change. So when there is deforestation, the emissions from deforestation are counted in a different sector. And the reason we don't count it as in energy is we want to avoid double counting. So we just make the assumption that in energy that renewable fuels have no emissions, but if there are emissions associated with them, they would be recorded in another sector. So energy itself is divided into 3 parts. The bulk of the emissions are included under fuel combustion activities. However, other emissions can also occur during the production and transportation of fuels. or for instance, the flaring and venting of natural gas. These are called fugitive emissions. And emissions can also happen if there is CO2 capture and storage. It's not always 100% efficient, so there can be some leaks, and any emissions associated with that would also be counted here. However, as I mentioned, the bulk of the emissions are under fuel combustion activities, and that's what we use the energy balance to calculate the emissions from fuel combustion activities. So as mentioned, fuel combustion emissions represent over 65% of total global greenhouse gas emissions. So really the energy sector is really the key sector here. And you can see the importance of good quality energy data for calculating greenhouse gas emissions. So at the IEA, we calculate CO2 emissions estimate for most countries worldwide. And we do this using the base data submitted by the National Statistics Office. And these data are in physical units. So we convert them to a common unit, to an energy balance using the net calorific values, using the methodology I just described. And finally, having built an energy balance, we apply the fuel-specific emission factors provided in the IPCC guidelines to convert the energy data into CO2 emissions data. So as you can see, the hard part of all of this is really just building the energy balance. After you've built the balance, it's quite simple and straightforward to just convert the energy data into CO2 equivalent. So after building the balance, there isn't that much extra hard work to create a basic emissions estimate. In addition, I should also point out that countries submit their own emissions inventories as part of the Paris Agreement or the Kyoto process to the UNFCCC, in parallel. So how do we calculate emissions? As mentioned at the IEA, we apply fuel-specific emission factors provided in the 2006 IPCC guidelines. So you have a different factor for gasoline, for fuel oil, for diesel. Each fuel has its own specific factor. And we use these to convert the energy data into CO2 emissions data. Now, under the IPCC guidelines, there are 3 tiers of methodologies, kind of 3 parallel pathways by which you can calculate emissions estimates. Tier 1 is the most basic tier, and it uses default carbon emission factors for each fuel. So there's a single factor given, and you just apply that, say a single factor for gasoline, and you apply that to your gasoline consumption data to calculate your CO2 emissions from gasoline. And that's what the IEA uses. However, in tier 2 or tier 3, you could have country-specific or technology-specific emission factors. And they can produce a more accurate emissions estimate, but you need additional information on how the fuel is combusted or the technologies in a specific country, etc. So these factors, the second and third tiers are more accurate, but they require more information. So the reason that the IEA uses tier 1 is that it allows us to use a comparable methodology across all countries using just the basic fuel consumption data that's provided by the energy balance without necessarily needing to know additional details on how the fuel was burned. However, when countries themselves are submitting their inventories to the UNFCCC, they are encouraged to use higher tier methods when possible. So under the tier 1 methodology, we simply take the fuel consumption data for each fuel and multiply it across by the basic tier 1 fuel-specific carbon emission factor provided in the guidelines. And then we sum the emissions across all fuels and all sectors to obtain the total CO2 emissions estimate for a country. So, as I mentioned, emission factors differ by fuel. As Gianluca showed in one of his questions, generally coal emits more CO2 emissions per unit of energy than oil. So we have coal here, oil, and finally natural gas. So you can see here that natural gas has a far lower emission factor than most of the other fuels. And that's why it's sometimes considered a transition fuel. Something that we can move from coal to gas and still create the same amount of electricity, but with a lower amount of CO2 emissions. And in fact, from an electricity generation perspective, the difference in emissions here is actually underestimated, as this shows emissions per unit of energy input, or emissions per unit of energy. However, natural gas plants have a higher efficiency typically than coal plants, so then they would use less gas per unit of electricity produced, so the difference in emissions would actually be slightly greater than is shown here. And of course, as I mentioned, renewable fuels such as renewable waste or biomass or charcoal, they do not have CO2 emissions estimates. They are not counted as CO2 emissions from fuel combustion. However, in fact, the guidelines do have emission factors. So if you wanted to, you could calculate emissions from those fuels. They're just simply not included in CO2 emissions from fuel combustion. However, they can be calculated and mentioned as a memo item at the bottom of the CO2 emissions estimate if you want. So to conclude on the section on CO2, human influence on the planet system is clear. The energy sector is responsible for the bulk of global CO2 emissions, over 60%. Therefore, all countries, big and small, developed and developing, need to work together to build a sustainable energy future. In addition, I hope you all agree on the importance of good energy statistics and, of course, good calorific values in creating energy balances and, of course, CO2 emissions estimates. So thank you for your attention. And I guess now if you have any questions, we'll be happy to answer them.
Thank you, Aidan, for your very, very interesting and detailed explanation of energy balances calculation and also CO2 emissions. It was really interesting to listen to your expertise here. And I also invite, as you did, every participant to ask any question through the question and answer tool, if they have any. If not, you can also, as I said prior to other, in other webinars, you can send us an email and we will be able to answer your specific questions later on. But please do it now that Aidan is present if you have any important questions you want to raise. I see Sirak is saying thank you too much to everyone. Thank you very much to you, all the participants, of course, because I know it's not the most convenient time for all of you, but you have been present today. And I hope other thank you from Mr. Josef Melka. So just for logistic information, we will move the webinar that we are supposed to have tomorrow on modeling to Monday because of the Muslim holiday, and so the official and government offices will be closed tomorrow for most of you. Monday, so morning at, I hope at 11 is okay for you. If not, we can propose also at 10. But I have to verify with the speakers. Also, I will be sending to you today or tomorrow an exercise that you can start looking at, that we will start correcting together on a later webinar on next week on Wednesday. This exercise is about balances and energy statistics, but there is also part on energy modeling that you still didn't see because the webinar will be on Monday. But you can start looking at the exercise. And so when you have time, you can start trying to solve it or at least reasoning on that, so that on next Wednesday, Arnaud and myself can walk you through that and try to give a more, let's say, interactive and real life example of energy statistics and modeling exercises. I hope you all enjoyed. There is a question. 10 is better. Okay, Elias said 10 is better. Okay, we'll try to see 10 or 10:30. I will send an email anyway. If it's possible, we'll try that. I will check with the speaker because we'll have a modeling expert on Monday speaking. If he's available at 10 or 10:30, we will do definitely that. And then thank you very much again. enjoy the holiday tomorrow, or for the people that work tomorrow as well, enjoy your working day. And I hope you can apply what we are seeing together in your daily work and raise the importance of having energy statistics of high quality in your country. So thank you very much again, and see you on Monday, but please look at your emails because we will be sending more precise information about that soon today or earlier tomorrow morning. Thank you very much.